Right. So good afternoon, students. So today, later on, you will have your quiz 2. Okay? Same thing, multiple choice. I think maybe 10 questions or so. All right. So what happens is that we will cover the material, hopefully finish the topic on vector operations. Okay? By about 1:45 later. Okay, so 1:45 I will stop, and then you guys take a break. Okay, and then certainly we'll have our quiz starting exactly at 2 p.m. Okay, so that's the plan. All right, I got a request to go through this question on the quiz, the past year quiz 2 that I have uploaded on Monday. Because I think the number of you didn't understand the last question on the level set. So as you can see, the question is asking which of the following is a level set of the function below here. Okay, so the function is a function of 3 variables, right? But it doesn't matter. Really, just let the function be some constant c, right? Some constant c. Okay, so that's the level set, but of course none of the following options, none of the given options look something like that. Okay, because the question is asking, right, is a level set. So c can be anything. So now of course the question is, right, which of the following conforms to a value of c that could be in the range of this expression. Because remember, the constant c, right, has to be in the range of f, right? Or else how can you let the f equals to c if f cannot even attain the value of c in the first place? Meaning to say there is no such range. Okay? So therefore you need c to be in the range of f, right? So you can look at this exponential function, and you know that for exponential function, it will never be 0. It will be approaching 0. Right? And of course, as x, y, z goes very big, positive, let's say, then it will be infinity. Okay? So therefore, you can understand that this guy will be more than 0. Right? So the range of the exponential function is more than 0. And then the range of this entire expression will be more than 2. Because you plus 2, So therefore, this guy, right, will be more than 2. So which means c has to be more than 2 then, right? Because c has to be in the range. So c is more than 2. Okay? I think so far so good, right? So therefore, we can kind of like mess around with this thing, which is e to the xyz equals to c minus 2. Because if you look at the expressions given here, right, they seem to be all written in like some function of the inputs, meaning to say the independent variables, a relation involving only the independent variables x, y, z. Okay, so certainly you can manipulate this expression, right, into that form. So from here you can see that if you ln both sides, you get x, y, z equals to ln c minus 2. Okay? But because c minus 2, for c more than 2, so c minus 2 will be more than 0. Okay, right? So since c minus 2 is more than 0, then ln of something that is more than 0 will be an element of R. That means, meaning to say it can give you any number. Right? Because ln, right, the argument for ln must be positive. Okay, and c minus 2 is indeed always positive. So, you know, the ln function looks like that. So, this is a ln function. So, let's say this is your c minus 2 axis. Okay, so c minus 2 more than 0, a ln function can give you any number, any real number r. Okay, so therefore, from here you can see that, right, you can actually write it as z equals to ln c minus 2 divided by xy. Okay? Yeah. So therefore, actually, if you observe, right, this 3 over xy will conform to this form, where ln c minus 2 will be 3. Okay, so therefore, this is the correct answer. This is not the correct answer because z equals to xy. Z equals to xy is not like z equals to something over xy. So therefore, this option 4 cannot be the correct answer. Okay, then z equals to xy. Oh, so basically this is the same as this option. So you choose option 4, then I don't know, you should probably also choose option 2. So that's a hint telling you that option 2 and 4 is not the answer. Then after that, this is certainly to trick you because it's minus 2, but how can the exponential function give you something that is negative? Not possible. So therefore, the only possible answer and the correct answer will be option 3. Is that all right? Can Okay, so this is of course testing you on the understanding of level sets as well as the range of multivariable functions. Okay, so now we are going to continue with our vector operations. So we stopped at dot product. So the dot product is basically just computing how similar two vectors are in the sense of the directions they are pointing towards. So if two vectors, right, they are pointing in exactly the same direction, then they will give you the maximum dot product. Correspondingly, if they are pointing in totally opposite direction, then they give you a negative, that means the most negative dot product. Then if the two vectors are pointing in orthogonal or perpendicular directions, then they give you the 0 dot product. Okay, a dot product of being 0. So therefore, the so-called value of the dot product actually indicates how much similarity the vectors' directions have. Okay? So and then the dot product, right, actually very simple to compute. It is just the sum of the components multiplied together. Okay, so you can see very clearly, right, that if you take u1 times v1, then you just get the first term. So really is u1 times v1, that's the first component, multiplied together, u2 times v2, plus the second component, multiplied together, and so on, so forth, all the way until the last component. So which means that the dot product is only defined between two vectors, right, that have the same dimension. Okay, they have the same dimension. They have to have the same dimension, right? Or else you cannot possibly have the dot product being computed. Okay, so just take note that the dot product actually outputs a scalar value, right? Because you sum up all the products of the components, so therefore it's really just a number. Okay, so that number is a scalar, right? And it's also called the inner product. Okay, just fancy names. Okay, not important. Yeah, and then if you combine the two definitions of the dot product, right? One which is the sum here, right? So you can see that this sum, right, is one expression. This sum thing here is one expression, and then there's then the dot product is also looking at the projection, right? The projection of one vector onto the other vector. So therefore, if you link up the two expressions, so this is the original expression, right? Taking the projections, then you can actually isolate theta. Okay, so isolate theta, then you realize that actually it's just cosine inverse of the sum of the products of the components divided by the product of the magnitudes or the lengths of those vectors. Okay, so therefore this is a way, actually, this is a common way to find the angle between two vectors. Okay, because when we take dot product, actually we don't go and bother ourselves with finding the angle and whatnot, right? The reason is because we have the vectors in column vector notation. So to compute dot product, really we just use this operation. It's very straightforward. Okay? So let's take a look at an example. We have a force vector 4, minus 1, 3 acting on an object as it moves through a displacement of minus 2, minus 1, minus 2, minus 5, 1. You are supposed to determine the work done by the force and the angle between the two vectors and explain it, are the values logical. Okay? So actually this is a three-dimensional vector. So what happens is that, let's say we have this object, Okay, and then there is a force. So maybe you have some force vector. This is your force vector F. Okay, and then it is moving through, acting on the object, and then it is moving through a displacement vector of -2, -5, 1. So therefore, F in this case will be 4, -1, 3. But the displacement is not in the same direction of the force. Okay, I'm not exactly sure what this displacement is, but maybe I'm just going to say that this green vector is the displacement vector, D. And then this guy is equivalent to -2, -5, 1. Okay? So we have a mass, an object, and then the force is acting on the mass, and the mass actually moves the displacement D. Okay, so we're supposed to determine the work done. Now, in your physics, you have probably learned this before. Have you? That the work done in this case, you're not supposed to take force times distance move. Not force times distance move, because the force is not in the direction of the distance. So therefore, the work done, right, has to be, the dot product between the force to the distance. Okay? Why? Because you always need to resolve, correct or not? You need to resolve. So you resolve the force vector into the direction of the displacement vector. Then you multiply that. But that is as good as taking dot product, what? Isn't that correct? Okay? So which means this work done, right, is really just force dot the displacement vector. Okay? So this is trivia, which is 4, -1, 3 dot -2, -5, 1. Okay? So if you compute this, right, it's really just 4 times -2 minus 1 times -5 plus 3 times 1. Okay? So therefore, you are going to get like -8 plus 5 plus 3, which is 0. So the work done actually is 0 by this force. Okay, and because the dot product is 0, since the dot product is 0, then the angle between the two vectors F and D must be what? Must be perpendicular, must be 90 degrees. Okay, because you can see that, right? Cosine, or rather, straight away you find the theta between them. So theta, so where's theta? If I project this force, right? So let me project the force. Okay, hold on. Yeah, so if you project the force, then I can identify that theta. So this is theta. Correct or not? That is the angle between the force vector and the displacement vector, theta, this black angle here. So therefore, this must be what? Cosine inverse. So cosine inverse what? F dot D divided by the magnitude of F multiplied to the magnitude of D. But magnitudes cannot be 0. So in this case, the numerator being 0 will give you an inverse cosine of 0. So therefore, inverse cosine of 0 is exactly pi over 2, which is 90 degrees. Is that right? Okay. So obviously, the zero work done, right, must agree with the theta being pi over 2. Okay, it means to say something. It means to say that, right, this force, even though it's acting on the mass, is not responsible for the displacement of this mass. It's not responsible for this displacement. This displacement is caused by some other effects or some other forces. Nothing to do with this force. Okay, because this angle is actually perpendicular. Is that alright? Okay, so maybe we can just give a reason. So, logical, since F is perpendicular to D. Okay, so the work done has to be 0. So the values must agree. in this case. Can Any questions? Good. Right, so this will be the properties of the dot product. Okay, so the first one is just u dot v equals to v dot u. Doesn't matter which you dot first or second, right? The reason is because it's still u1 v1 plus u2 v2 and so on and so forth. Okay, so the dot product is also distributive, right? This one you can check easily. Then this guy, right, the third one, you can actually multiply the dot product with a constant k, and the constant k will just carry over, okay, to the final result of the dot product. Then the zero vector dot any other vector will be the zero value, will give you zero value, okay, because 0 times u1 plus 0 times u2 and so on and so forth. Obviously you get 0. Okay, this is something interesting. So u dot u equals to the magnitude square. So this one should be easily provable, right? Because if you have u dot u, so it really means like u1, u2, u3. Of course, you can have more components, doesn't matter. 3 components will be enough to show. So if you do the dot product between u and itself, then you're going to get u1 square plus u2 square plus u3 square. Okay, but this is really the square of the square root of u1 square plus u2 square plus u3 square. But the square root of this is actually the magnitude. So it's really the magnitude of u whole thing square. Okay? So therefore you just prove left hand side equals to right hand side. Is that alright? So if you take the dot product of a vector n itself, right, then really you can get the square of the length. Can Okay? And then actually for 6, right, this one easy also. Okay, 1 to 4 is very easy, too easy probably. Okay, then this 6 is also very easy because it just makes use of matrix multiplication, right? So if you have left hand side, so this one is u dot v, then u dot v is, let's say for example, u1 v1 plus u2 v2 plus u3 v3. Let's say 3 components. Then you can see that this guy is actually also equivalent to u1, u2, u3 transpose. So what's transpose? So this one transpose times v. v1, v2, v3. So the transpose of a matrix is just write as a column vector instead. Because column, write as a row vector instead. So column become row, that's the transpose. Okay, or row become column, that's also the transpose. So therefore, if you do it this way, so then you take matrix multiplication. So matrix multiplication is u1 times v1 plus u2 times v2 plus u3 times v3, right? So isn't this the same thing as u dot v? It's the same thing, okay? But you can also say that it's v transpose u. So if you have v transpose u, then you have v1, v2, v3 dot u1, u2, u3. Also the same thing, it's just that you take v1 times u1 plus v2 times u2 plus v3 times u3. But you still get back this thing. So this will be giving you the 2 identities on the right hand side. Okay? So therefore this guy is actually u transpose v. U transpose v, and this guy will be v transpose u. Any objections? Is that right? Okay, so u dot v, you take the dot product, actually you can rewrite it as u transpose v or v transpose u. They are the same thing. Because eventually you just get the sum of the components multiplied together, that's all. Just like different ways of writing the same operation. Okay? So now we move on to cross product. Okay, so cross product is an operation between two vectors that is going to give you a third vector that is perpendicular to the two original vectors. Okay, of course that sounds a mouthful, but if you look at the diagram here, right, you'll see why. You see, A cross B. So there is a plane here that contains A and B. Okay, so therefore A cross B is going to give you the third vector, whereby this A cross B vector, right, is going to be perpendicular to vectors A and B. It's going to be perpendicular to vectors A and B. Okay, which implies that it is also going to be perpendicular to the plane containing A and B. Make sense, huh? Okay? So therefore it's like quite easy to understand, right? Because let's say if you have a plane, so let's say this is the screen is the plane, right? So the A cross B vector, where A and B are on this plane. Okay, let's say on this plane. So the cross product is going to give you the third vector, right? And the resultant vector that is pointing out of the plane. Okay? So therefore the cross product, what is the direction? So there's a convention. The convention is, right, you have to use your right hand. I mean, there are multiple ways, but the way that I propose is using your right hand. It's called the right hand rule. So it's like that. So you say A, like that, right? So A cross B. A cross B, right? So if you imagine this plane, right, let's say is a horizontal plane. It's a horizontal plane. So you do A cross B. A cross B, your thumb, right, pointing upwards. So this is A cross B. That's the direction. Then the other way is B cross A. What about B cross A? Can also. B cross A. B cross A. You can see the thumb pointing downwards. So this guy is B cross A. Don't use both hands. Use both hands, right? You'll mess up the direction. You'll be lost. Hey, this one never learned yet, your physics. This one is rotational motion. Torque, moment, bending moment, torque. The torque of a force, turning effect of a force. Haven't learned yet? Not yet covered? Okay, so you'll be probably, no, I thought it should be covered. Should be covering your rotational motion already. Covered it, Can, Okay, some people like to use the three-finger method. Okay? So because I cannot remember which finger represents which, so therefore I don't prefer this method. I prefer the curling method. Okay, so what's the reason for learning the cross product? Okay, just like the dot product. Dot product, right, compute similarity in the direction of the vectors and also compute work done, which is energy consumption, for example. Cross product also got used. Cross product is to compute, as I mentioned earlier on, right, the bending moment, the torque, turning effect of a force, or the rotational motion. Okay, so anything got to do with rotational motion, right, you might need to compute a cross product. Okay, later on in topic 7, you will see that the cross product is used to compute the twisting effect of a force field. Okay, that means when you put an item on an object, right, into a force field, right, that force field will cause that item to twist around. Okay, something like a tornado. A tornado, right, inside the so-called cross product is non-zero. Okay, so we'll be looking at that in topic 7, right, which is why I need to cover this. Or rather topic 8. Okay? Yeah, so actually if you look at the formula, it is very similar to the dot product, if you realize. Cross product is still taking the magnitudes, but now you multiply by sine of theta. Okay, you multiply by sine of theta instead of cosine theta, and then you also multiply by the unit vector n that is perpendicular to the plane containing the original vectors A and B. Okay? So it is this n, right, that gives you the directional sense of the cross product. Okay? But what is the deal with this sine theta thing? Now you can see that sine theta if I draw the two vectors, you will see it quite clearly. So you can see that, let's say this is vector B, and let's say this is vector A. So theta is still the angle between the two vectors. But sine A, actually, you are looking at the projection of A onto the perpendicular of B. So therefore, there is a perpendicular here. There is a perpendicular here. This perpendicular. Okay? So therefore, actually, this length is A sine B. Oh, sorry, A sine theta. Sorry, the color here is not very clear. Maybe I use green. Can you see? Opposite, this green line, right? The length of the green vector here is opposite to theta. So therefore, it's sine, Okay? So you can see that this component is actually A sine theta. So you take A sine theta, go and multiply by the length of B. So therefore, this seems like trying to compute the degree of perpendicularity between the two vectors. Is that all right? Okay? So therefore, what values does the magnitude of the cross product give for the angles below? So if your angle is 0, because your sine 0 is 0, what? So therefore, this guy will be giving you the 0 vector. Since sine 0 equals to 0. Okay? Because your cross product here, right? A cross B is magnitude of A times magnitude of B times sine theta. Then times the perpendicular vector n. Okay? N is perpendicular to A and B. So if your sine theta is 0, then you have a 0 times n. So 0 times n, right, will be just a 0 vector. Okay, a vector of all zeros. So then what about pi over 2? Well, pi over 2, your sine pi over 2 is 1, what? Correct or not? So therefore, the magnitude, oh sorry, my bad. This one is magnitude, so it will be 0 instead of a 0 vector. Okay? Because the magnitude, right, is just this part. The magnitude. Okay? Didn't times the vector n, so therefore it's just 0 value. Then the second one, right, is just the magnitude of A times the magnitude of B. So obviously the reason is sine pi over 2 is 1. Then when you have pi angles between the two vectors, so that will be what? 0 as well. Because sine pi also 0, what? So let me just draw the vectors for clarity. So this one, two vectors pointing in the same direction. No perpendicularity. So if two vectors, no perpendicularity at all, then it is 0. Then these two vectors, perfect perpendicularity. The two vectors are perpendicular to each other. Then you got maximum cross product magnitude. Then the third one, right, the two vectors actually pointing in the opposite direction because it's pi. So therefore there is no perpendicularity at all. Because this angle is pi, what? 180 degrees. Okay? So therefore, if it's 0 to pi, in between 0 and pi, then obviously you get some positive value. So this is like more than 0. Because sine 0 to pi is positive, So therefore you can say sine x, right? Sine x, or rather sine theta. Sine theta is more than 0. For theta that is in 0 to pi. Because you are looking at the projection onto the positive y-axis. That's your sine. Okay, right? Okay? So therefore, what's the layman description of the characteristic of the of the cross product? So I think this one we can write down. So the cross product computes the degree of perpendicularity perpendicularity, okay, of two vectors. Is that all right? Okay? So maximum cross product magnitude, right, will happen when the two vectors are perfectly perpendicular. Is that okay? Okay, so you can see that this one actually like a brother or sister of the dot product. Dot product is compute similarity, right? That meaning to say, right, whether the two vectors, right, are they pointing in the same direction or not. This one is like compute how different in direction does the two vectors point. If it's totally different, like totally perpendicular, then the cross product will be maximized, giving you the magnitudes multiplied together. Can Yeah, so actually to compute the cross product, so this is a irritating operation. It's not as nice as the dot product. Okay, so there are many ways of computing the cross product, but this is what I prefer. Okay, some of you use the IJK thing. Okay, it's up to you. I don't care what you use. Okay, but I'm just going to introduce you what I prefer. Okay, because the vectors are usually given in column vector notation, as you can see. So how to compute the resultant vector that is perpendicular to both A and B? Now, you have to cover, let's say this first component, right? So what you do, this is operational wise. So you have covering the first row. Then after that, right, you take this A2 multiplied by B3 times, minus of A3 multiplied by B2. So you can see the cross operation here. Okay, that's why it's called the cross product. So therefore you can see A2 times B3 minus A3 times B2, represented by the cross or arrows here. Is that right? Yeah. Okay, so that's for the first row. Now then if you do the second row, right, same thing, but the second row have to add a negative. So there's a reason for that. Okay, I'll explain later on. But if you look at the second row, this second row, right, to cover the second row, same thing. Then you take A1 cross to B3. Then A3 cross to B1. Take the difference between them. You see? A1 B3 minus A3 B1. Okay, but for second row, you must remember to put the minus. You see? Okay, so then for the third row, it's the same as the first row. For the third row. So you cover the third row. Then you take A1 cross to B2 minus A2 cross to B1. So therefore, A1 B2 minus A2 B1. Is that right? Okay, so you can see the cross operation here, right? So therefore, it's called cross product. Okay? So this one just operation. So let's look at the exercise. Compute the cross products of 310 and 020 in both directions and sketch the resultant vectors. What did you notice about their directions? Okay, so 310 cross 020. Okay? So first row, cover the first row. I mean, just like imagine you're covering the first row. So just look at the second and the third row. 1 times 0. So let me write down the full operation. So it's 1 times 0 minus 0 times 2. Second row, I must put a minus first. Then I put bracket. Okay, then 3 times 0. 3 times 0 minus 0 times 0. Then third row, cover the last row. 3 times 2 minus 1 times 0. So what's the resultant? Compute this. So you're going to have 0, 0, 6. Is that right? Simple operation. Okay? So now let's take a look at the other one. 020 cross 310. So same thing. Cover the first row. 2 times 0 minus 0 times 1. Then second row I must put minus, put bracket. 0 times 0 minus 0 times 3. Last row, cover the last row. 0 times 1 minus 2 times 3. So you compute that. The answer is 0, 0 minus 6. Is it alright? Can Okay? So obviously, right, if the top is A cross B, if the top operation, right, is A cross B, then this is A cross B. The resultant vector is A cross B. Then you can see that this is obviously B cross A. This operation is B cross A. But clearly, B cross A equals to the negative of A cross B. Okay, through this example. Right? And we can, of course, prove it easily just by having generic components like x, y, z, for example. Okay? Because you can always extract a negative out of all three components, and therefore you have a negative here. Okay? It's quite easily to prove. It's quite easy to prove. So, what do you notice about the directions? Okay. You notice that 0, 0, 6, right? And you look at the two vectors here. Now, if you were to visualize the vectors in 3D space, then you will see why is it that the vectors are as such. You see this 3, 1, 0. So your 3, 1, 0 vector A, right, must be what? Must be on the xy plane, because it's 3, 1, 0 what? There's no z component. So that means there is a vector here that is on the xy plane, 3, 1, 0. Okay, so let me write on xy plane. No objections, right? 3, 1, 0 must be on the xy plane. No z component. Then 0, 2, 0 is what? 0, 2, 0 is in the y direction only. So this is 0, 2, 0. Because it's only y axis, what? The y component is 2. Then the x and z component 0. So what is the plane that is perpendicular to the two vectors here? Sorry, what is the plane that is containing the two vectors here? Must be the xy plane, what? So therefore, what's the resultant? The resultant, you notice, is 0, 0, 6, right? Which means that it is on the z-axis. Can you see that? This guy is 0, 0, 6. And very clearly, 0, 0, 6 must be perpendicular to the y-axis, must also be perpendicular to the xy plane. Can you observe, right? So this 0, 0, 6 is perpendicular to both vectors A and B. Okay? Any questions? Can Because just now we started off by saying that the cross product is going to give you a resultant vector that is perpendicular to the original vectors. Okay? And in this case, through this example, we can easily observe that. Is that okay? Questions on the cross product? Good. Okay, so this will be the properties of the cross product, which I will not go through in detail. You can check each and every one of them on your own. It's kind of straightforward. Okay, so this is the end for this recap. So as I mentioned before, actually in the GPT, right, your generative pre-trained transformer, you have this scaled dot product that computes the so-called context or attention between any two words in whatever question or paragraph that you have entered into ChatGPT or any other LLM. Okay? Right, so if you are interested in the derivation of the cross product, I have added the two slides here. Okay, but of course the derivation will not be tested. You just need to know how to compute cross product can already. Okay, and not to worry at this stage, because in topic 8, right, you are definitely going to compute the cross product. Okay, as part of other operations. So therefore, I think you will have more practice in topic 8. Questions? Okay, good. So, I'm glad I finished. So I'm going to stop here. You have 15 minutes to rest. Yeah. I also need you to... Okay, we will start exactly at 2 p.m. Okay, so you can go and have a good break, but you come back at 2 p.m. Or you come back before 2 p.m. Right, but I'll need you to do the module and teaching feedback. Okay, so let me give you the link. Give me a minute.